Hello, everybody, and welcome to our webinar today on using VSim to simulate inductively coupled plasma. My name is Colleen Dunn, and I just want to welcome you all today. We are very excited to have Dr. Eve Lanham as our main presenter. She received her PhD in 2022 as a student of Professor Mark Kushner with her thesis on modeling pulsed inductively coupled plasmas. After graduating, she joined TechX and became the lead developer of the new implicit EM solver under the mentorship of Dr. John Carey. After her presentation, we will have a brief demonstration of the ICP solver in our VSim 12.2 release that is coming today. And with that, let's go ahead and get started.
Thank you, Colleen, for the introduction. I am Dr. Eve Lanham, and this work was carried out primarily by me and Professor Carey. But this has really been a team effort at TechX. And today we'll be talking about our inductively coupled plasma example. Brief outline of this talk is I'll give a general background of inductively coupled plasmas and their uses, an overview of our example in VSim 12. The example is called 2D inductively coupled plasma with shapes, and we'll talk in depth about that, as well as about future work, where we will be presenting more on the inductively coupled plasma, and end with some concluding remarks. Inductively coupled plasmas are a very common plasma source used in many different industries. The inductive in inductively coupled plasma means that power is electromagnetically coupled to drive the discharge. Typically, this features an antenna that's external to the plasma that is supplied with current. It drives the magnetic field and induces an electric field. This electric field accelerates electrons and heats the plasma through what is called ohmic heating. This means that energy is transferred from these fields to the plasma through electron impact collisions. These types of plasma chambers typically add a separate power source, such as a bias, underneath a wafer for processing to control the flux and energy of ions. Modeling an inductively coupled plasma is a difficult problem. So here's an example inductively coupled plasma chamber. Here's a cross section showing the antenna above a window and a lower electrode here. An azimuthal current, which means in and out of the plane, is used to model the antenna above a dielectric disc. So here the window is treated as a dielectric. The radius is limited by conducting sidewalls, so typically you'll have ground around the chamber, and the wafer sits at the bottom on top of an electrode. The discharge is driven by a supplied current to the antenna, which drives the induced electric field in the plasma. The oscillating fields have feedback with each other, and it creates a plasma outflow, which creates a potential that is greater inside the plasma than compared to ground. So why would you want to use particle in cell to model inductively coupled plasmas? Fluid-based approaches to modeling these types of discharges generally make assumptions of local power deposition. This means that the plasma typically is in equilibrium with the local electric field. So this means that the assumption will break down when moving to lower pressure because power really is only removed from the field due to collisions between particles. When the mean free path needs to be resolved on the mesh, and the time step needs to be low enough to allow for resolving the collision frequency. Why are these fully kinetic approaches not more commonplace? The main reason is because simulations may take too long to resolve the problem that you want. Typically, ICPs are driven with relatively low frequencies, such as 13.56 megahertz, and traditional kinetic modeling using PIC dictates that the time step needs to be limited by the speed of light, and resolving that on the mesh at that frequency means that you would need to take an intractable number of time steps to solve the problem. Additionally, time domain modeling is sensitive to noise, and that can be a big factor for all types of problems, but specifically ICP. Our solution to these approaches is to use an implicit solve in cylindrical coordinates with a smooth turn on to avoid noise. Now I will introduce to you our new VSim plasma example called 2D inductively coupled plasma with shapes. This example requires multiple different types of physics to simulate. Particle kinetics are needed to resolve the sheaths and dynamics. The chemistry is very important because this discharge is sustained through ionization, and modeling some of this chemistry with fluids is also important. We have complex surfaces and materials that need to be resolved. A lot of the plasma is determined by electrostatics, but with the addition of an antenna, we need to have the electromagnetics also resolved. The main feature of this example is a new implicit solver to model current sources, specifically for 2D cylindrical coordinates. And now I will give a brief overview of the algorithm that we use to solve inductively coupled plasma problems. This is specific for cylindrical coordinates. We have our new proprietary implicit solver to treat our electromagnetic solve. We have J theta set from the antenna and particles deposit to J theta. And we have Ampere and Faraday updaters to get BR, BZ, and E theta. In addition to this, for this example, we do an electrostatic solve. This is just Poisson's equation using our proprietary cut cell framework. This solve gives us the electric potential and the electric fields in the R and Z direction. Particles are then used to interpolate the fields to their position, do collisions using our DSMC framework. Particles are pushed and deposit their current to the grid. This procedure iterates back and forth each time step, and our implicit solve typically converges in less than 10 iterations, and you can use whatever method you want. Something like GMRes is typical, or you can use conjugate gradient methods as well for the solve. This slide shows our new implicit EM solver in a vacuum for 200 by 199 cells at 13.56 megahertz. Here we're just taking 20 time steps per RF period, and we're showing a movie of what the electric field looks like. The current is set in this box here, which corresponds to here, and we see that the EM solver is stable. If we wanted to do an explicit EM solve over the same time scale, we would need to take approximately 5,000 more time steps. So this means that we potentially have up to a 5,000 times speed up using our new implicit solve. Now I'm going to introduce the 2D inductively coupled plasma with shapes example. The geometry is based off a GEC reference cell in the ICP configuration. That just includes an antenna above the dielectric window. Chemistry is pretty simple based off of the Turner benchmark, which we have another example on. This features electrons, helium ions, and 6 collisional processes. Materials in the simulation are defined as shapes using CSG. And here we have multiple dielectrics, such as a wafer, the dielectric window, and the focus ring. We have several metals, such as the ground shield, the powered bias, which is below the wafer, and the antenna. Current source is also the antenna. We have a metal wall boundary around the outside. And these metal boundaries have potential specified as Dirichlet boundary conditions, a visual setup. Dielectrics are defined with the material relative permittivity and Neumann boundary conditions automatically in the code. And particle absorbers are specified on all materials. These are the simulation conditions for the ICP example. We initialize the plasma. We initialize particles in the plasma, 10 particles per cell at 192 by 256 cells with the same, we have DT is set to 9.2 times 10 to the negative 11 seconds. The neutral density is this with a 300 Kelvin temperature, which corresponds to about 100 millitorr pressure. The antenna is set to 100 amps at 13.56 megahertz, ramped. And we initialize the plasma density, the particle weights to give about 5 times 10 to the 14 per meter cubed, electron density and ion density. Electrons get an initial 2.58 EV temperature and ions are set to 300 Kelvin. The simulation runs for 2 RF cycles or 1600 time steps, and we're showing results for dump 40. This takes about 10 minutes on a MacBook Pro, so it's something that you could run on a laptop quite easily. Electrons are accelerated by the azimuthal electric field and produce localized heating in the plasma, shown here beneath the antenna. We are plotting the electron positions, and the color indicates their energy, so up to 15 eV. Sheaths form between the plasma material boundaries because the electrons are hotter and more mobile and can diffuse out of the plasma much quicker than ions. Here we're taking a more in-depth look at the induced electric field. This is a snapshot at dump 40 of the azimuthal electric field generated by the antenna current, and it penetrates into the plasma within 1 electromagnetic skin depth. The electric field E theta that's generated from the antenna current. As you can see here, it peaks around the antenna and decays as you move into the plasma. The electric field is absorbed within about 1 electromagnetic skin depth of the plasma, and this is what you would expect to see. We have some slight oscillations or noise in the field due to particles, but overall, we see exactly what you would want to see in the electric field. The electric potential also looks how you would expect. Electrons are heated from the induced field and diffuse out of the plasma faster than ions, creating a positive plasma potential. Inside the plasma, the potential is fairly uniform, which is what you would expect in only 2 RF cycles. But you can see the geometry has the potential set to ground where it should be, and Neumann boundary conditions are featured for the focus ring and this wall gap. We can also take a closer look at the electric potential produced in the plasma. Electrons heated from the induced field diffuse out of the plasma faster than ions, creating a uniform positive plasma potential. You can also see that materials set to metal are set to ground, 0 voltage. We also have the antenna set to 0 voltage for now. That can be specified by the user to also model capacitive coupling from the antenna. The previous data is all for a single time step at the end of the simulation, but to look at time history data, we can do something like looking at a probe. The simulation also has time history saved at a position in the plasma, have Z equals 0.05 and R equals 0.067 meters. On the left, we're showing the induced field E theta. It ramps for the first RF cycle and then oscillates as expected for the second. The electric potential is shown on the right, and within 2 RF cycles, it saturates to around 170 volts as sheaths develop as in the plasma diffuses. The example can also be expanded on by adding an RF bias. Previous simulation had a 0-volt bias, and here we added 100 volt at 13.56 megahertz. Here we're just showing dump 35, which shows the electric field potential at a minimum. So we have 100 volts on the bias, and this is what the potential looks like in the plasma. Looking at the time history for the probe for the simulation with an RF bias, we see that on the left, the E theta that's generated throughout the simulation is near identical to the azimuthal electric field without a bias because the plasma is near identical. This is what you would expect. So the bias does not have an influence or much of an influence on E theta. And the electric potential clearly oscillates with the bias, showing increases up to almost 200 volts compared to 170 without a bias. Future work will be discussed at GEC 2023, discussing evaluating power deposition in inductively coupled plasma systems using VSim. At AVS, we have a presentation by Daniel Main titled Kinetic Modeling of Wafer Processing Chambers in CCP and Coupled ICP CCP Systems using VSim. And we are also hosting TechX Worldwide Simulation Summit in October, and feel free to register when you can. In conclusion, we introduced ICPs and gave motivation to using kinetic approaches for modeling ICPs, specifically using VSim. I gave you an overview of our inductively coupled plasma example. It features a new implicit EM solver for current sources in cylindrical coordinates. We have geometry-defined materials, a stable implicit EM solve for current sources that can locally heat electrons and capture the physics of ICP discharges. Using our new implicit EM solver, we have a potential speedup of up to 5,000 times over running full EM simulations. We will have a further demonstration of using this implicit EM solver to model inductively coupled plasmas in October at several events, including GEC, AVS, and TWIS. And we are also working on a publication. Thank you very much for attending this webinar. Now we will have a demonstration of this example from Dr. Daniel Murray.
Thank you very much for that fantastic introduction to inductively coupled plasmas. A fair amount of new information for myself as I come from astrophysical plasmas. So I will be walking us through how to open this new ICP example and walk through some of the physics of it, what conditions you need to meet, and some of the physics that you can visualize after having run the example. So we can see here in the recent simulations on the Welcome tab that I've recently had several ICP cylindrical shapes opened. If you want to open it from a new example, we can click New from Example, go to VSim for plasma discharges, select the new section, Inductively Coupled Plasmas, and there you can see the 2D inductively coupled plasma with shapes. Say Choose, you can create a new folder and save it there. I am going to simply open one of my previous ICP cylindrical shapes. VSim will then take me to the Setup tab. And so right away on the right-hand side here, we can see some of the geometry that Dr. Lantham was describing. The orientation for this is the z-axis is extending horizontally, and then the r-axis is both vertical and in and out of the page, as this is a cylindrical example. So in order to use the implicit electromagnetic solver for any simulation, including any that you may want to set up for yourself, there are two key pieces currently that must be fit. The first is that you must choose that the dimensionality is 2 from the drop-down menu, and then in addition to that, that the coordinate system is chosen to be cylindrical rather than Cartesian. When you do that, going to the field solver in the basic settings, you will then be able to choose the implicit electromagnetic solver in the drop-down menu. A couple of things that I would like to note is, as we look at the geometries on the right here, we can see some of the constructive geometries that Dr. Lantham had mentioned earlier, including the wafer itself, which is this thin strip on the left side or near z equals 0. Just below it is the bias right here, which is chosen to have a material of PEC. We can see the window, which has a material of bottle glass, the antenna that will be doing the driving, which again is a PEC, and then also we can see the little probe for the history right there at the coordinates that Dr. Lantham had described earlier. Now, I will also touch upon, she had mentioned the boundary conditions during her talk, but I will just reiterate here that in upper Z, this boundary here is chosen to be a Dirichlet boundary with a voltage of 0, and same for upper R, as you expect for those metal boundaries. The ground shield is also set to have a voltage of 0 as Dirichlet. The antenna, as she had mentioned, is also set to 0. Now, the one piece that can be changed by the user if they wanted to change the bias voltage, we can see right here that it's set to a space-time function, bias voltage, which is really just the RF voltage times sine omega t. And I will show everybody currently, by default, the RF voltage is set to 0. So there's no actual bias when you first, by default, open and run the example. She showed some data where she had changed the RF voltage to be 100 volts, and so you, the end user, may also freely play with this parameter. In addition to the field boundary conditions, another thing I would like to mention is that in VSim 12.2, we are also releasing an analyzer called Compute AED, which is looking to compute the angle distribution and the energy distribution of whatever it is that you would like that history to record. So in this case here, we have another history set up to compute the AED for the helium ions as they hit the wafer and impact it. So with this setup, we would then go to our Run tab. We can see that the number of steps is set to be 1600. I believe Dr. Lantham had mentioned that we currently have it set so that there are 800 time steps per RF cycle. So this is running for 2 RFs, and we have a dump periodicity of every 40 steps, which means that we will have 20 dumps across a single RF cycle, and so we'll end up with a total of 40 dumps. You can choose how many cores you wish to run on if you switch over to the run mode, whether it be serial, parallel on your local machine, or if you're able to submit to a cluster, there is also a scheduler option. Now we can see over here in the actual engine log, I have previously run this example. And one thing to note is, as it says at the bottom here, on 8 cores, the total simulation wall clock time was 540 seconds. So it's just shy of 10 minutes, which is really honestly quite nice. So before I go to analyzing any of the results or visualizing them, I would first like to run through our compute AED analyzer and just run through some of the values that have been chosen for this. So there are quite a few values that the user must provide, but hopefully after I walk through them, they all make sense. So the first one is just providing the simulation name and the species that you would like to run this analysis on for the angle and energy deposition. You are allowed to and must choose a start time and an end time. In this case here, I have chosen the start time that corresponds to step 800, or basically at the start of the second RF cycle. And I chose my end time to be at step 1600, or at the end of that second RF cycle. So I'm currently analyzing just one RF cycle across. The lower and upper positions are for the surface that you are doing this history for. So in this case, we had chosen that the history would be attached to the wafer because we wanted to analyze what is the angular and energy distribution of the helium ions that are hitting or impacting the wafer. And so I choose just above the z-axis, but on the wafer, and then the upper position is the upper edge or end of the wafer. The analyzer requires the history name, which in this case matches the history name that I had chosen earlier on in the setup tab here, the compute AED HE1. And then you have a couple choices as to how many bins do you want for your energy distribution and how many bins do you want for your angle distribution. One key constraint is for the number of angle bins. There is a division over the sign of the number of bins, and so the end user must choose an even number of bins there. For obtaining the energy distribution, the end user is required to provide the lowest energy to bin in electron volts and an upper energy to bin in electron volts. Here I've chosen 0 and 130. 130 electron volts is actually a little bit above what we'll see for the helium ions, but that's just because I want to see that value drop to 0 as far as the total number of particles in that energy bin. For the lower and upper angle, it's similar for the lower and upper energy. It's how wide do you want to go? In this case, I've chosen -10 degrees and +10 degrees. And finally, there is the number of dimensions of the simulation. In our case, it is 2D cylindrical, so 2. And it would like to know the perpendicular direction, i.e. the normal, from the surface that you are collecting your charges on. In our case, that is +z. Because if I come back to our setup tab and we look at where our wafer is, we can see that the normal to the wafer is in the +z direction. With all of these values in, I can click Analyze, and it will generate two 1D sets of bins for the energy and angular distribution. So how about we visualize these results? So VSim loads up all of the data that we dumped, including the new analyzer results. And I'll start with our data overview, which is currently swapped from the images that Dr. Lantham had shown. So I'm just going to swap our coordinates here. VSim will take a moment as it reorganizes for itself where everything is. And let me preserve the aspect ratio. And so what are we looking at? I think the first thing to do is make this image a little bit easier to see. So I have in here several individual blocks. This is the antenna right here. This is the window right there. And then we have the wafer down here near the z-axis, the bias just below it, the focus ring, and the ground shield, and then the small wall gap over to the large R metal wall. So what I have plotted is phi, and on top of that, I will first plot the helium ions, maybe make them a little bit bigger, and then I'll shrink them again later. We can see that the helium ions reach over to the far wall and are impacting on top of the wafer directly, whereas if I plot the electrons, so we can see that the helium ions are slowly diffusing out to the grounded wall or into the wafer at the bottom. Recall that the bias below it does not have a voltage associated with it in this run, whereas the electrons are being drawn in towards the higher potential in the center of the plasma. And so you end up with the creation of these sheaths above the wafer and at the outer boundary of the system. Just like to show folks that you can also generate the images that Dr. Lantham had produced in her talk. This is, again, just quickly resetting the image so that way I have my radius on the horizontal axis. We can see that we end up with the results that she presented earlier, in that we see there is a rather smooth curve for the driven electric field in theta, along with some noise due to particles out at the edges. Here I am also presenting the same image that Dr. Lantham had produced earlier in one of her slides. This is the phi potential, again with the line out cutting straight through the antenna, the wafer, and the bias on the far side. And so we can see with the image on the right, we have the ground of the bias along with the potential from the wafer cutting into the sheath here, and then finally the bulk of the plasma coming out the far side. There is the sheath again here just prior to the window, the dielectric window, which is this sort of linear portion here, and then this lower drop is the ground because again the antenna is set to have 0 voltage. And finally, from the compute AED analyzer that we ran earlier, we can see the 1D fields for what the angular distribution of helium ions looks like impacting the wafer, as well as the binning for the energy distribution of those ions. So that is the ICP example. Again, I would like to remind everybody that there will be some future work on this, including a talk by Dr. Eve Lantham at GEC 2023 this year, as well as a talk by Dr. Daniel Main at AVS. And finally, we are also hosting our TechX Worldwide Simulation Summit in October on the 16th and 17th. And so with that, I would like to open it up for any questions that people may have for Dr. Lantham or the rest of the team here at TechX. Thank you.
Thank you, Dan. That was awesome. And we actually have a list of questions here that I want to ask. So people have been submitting them throughout the talk. But gosh, what a fantastic presentation that you guys just gave us today. I want to let everyone know that the new implicit EM solver that is critical to modeling the ICP plasmas is going to be in VSim 12.2, which is actually being released today. If this is something that you want to try, what you'll need to do, if you have been working with us, if you are a current customer, you can simply send us an email to sales@txcorp.com or to any of your contacts here, and we will help you with getting a download of the latest version. And if you have not evaluated with us before, or if it's been a while, there is an evaluation request form on our website. We will do our best to get all of those out today and tomorrow. It may take us just a bit. We anticipate having quite a few that we need to work with today. So having said that, on to the questions. The very first question I have is, can the plasma generation converge in 2 RF periods?
Thank you for your question. The convergence of a plasma is very particular to the initialization. 2 RF periods is pretty short for a low temperature plasma. Realistically, you wouldn't be able to reach an equilibrium in the plasma generation over that time period. But as you can see from our simulation here, you can start from a uniform plasma and form sheets within that time scale. So yeah, next question.
The next question we have is 100-volt bias means superimposing 100 volt onto the coil radiating 13.5 megahertz. I think that's just a confirmation. Is that correct?
So the bias that we were putting in the simulation, that is actually a separate electrode that's underneath the wafer. So this would be for accelerating ions into the wafer for processing. However, you can also add a voltage on the antenna to model capacitive coupling from the antenna, which is important for resolving all the physics of inductively coupled plasmas.
Okay. Another question, is it possible to simulate non-cylindrical ICP sources, such as like linear or rectangular?
Currently, our example is set to require having cylindrical coordinates. We wrote the solver in a more general way, so it works in Cartesian coordinates. However, we haven't released that for general use yet. It might be something, if there's enough need for it, it could be something that we release in the future.
Okay. We have another question. Is it possible to simulate effects of a Faraday shield between coil and plasma?
The answer in short is yes. The specifics of how you would model that are tricky because an ideal Faraday shield would just completely block the penetration of EM fields into the plasma. However, a real shield has gaps and a finite depth. You can capture some of those effects with our code. Yeah.
Another question, what can I learn from simulations like this that I cannot learn from electrostatic simulations?
That's a good question. If you properly treat the simulation electrostatically, you could get a very good approximation. But overall, it's not really self-consistent, and modeling the current source, the generation of the magnetic fields and the propagation of the electric field is pretty valuable. And we're able to capture some of the complexities that otherwise would be lost.
Another question, could this also be used to simulate an electron cyclotron resonance plasma source?
Thank you for the question. ECR plasmas typically operate at the gigahertz frequency, which would mitigate some of the usefulness for our implicit salt because you have to resolve the oscillations. So with running an ECR plasma, you're already pretty high frequency and it might be difficult to simulate in a short amount of time. But conceptually, it should work. Yeah, there's just some caveats.
Okay, there always are, right? Is there any limit to how small or how large the time step can be in these simulations?
The major limitation on the time step is dictated by having to resolve the RF period or the oscillations that you want. For example, when we're only resolving 13.56 megahertz, we showed that you can take 20 time steps and resolve that oscillation pretty smoothly. And that's the main limitation on the time step because the implicit solve itself is stable. Other factors that might change the time step are resolving the plasma dynamics, such as the collision frequency or plasma oscillations.
How was the 5,000 speed up estimated? You said you have to solve a linear system of equations instead of explicit update. Can you give some background on that?
Sure. So for most of our simulations, the timing is actually dominated by particles. So the particle push and deposit, as well as collisions, take up the majority of the time. Solving the linear solves for the fields are actually almost free. So being able to take larger time steps, and that's how we estimated the speed up.
Okay. Another question, how much larger than the average Debye length, if at all, are the spatial cells?
For this example, we chose the grid to resolve the Debye length. Obviously, the Debye length will change if there's more plasma being generated. You will have to take that into account for running simulations yourself. But solve itself is our main feature that we wanted to showcase here. But resolving the physics depends on picking parameters before the simulation starts.
Okay. The implicit update is both on fields and particles in the setup. Does the model support implicit electrostatics also?
Um,
Or implicit ES also?
the ES solve is also implicit. We have the solves for the electromagnetics and electrostatics are actually based off of the same framework and the same or similar matrices are set up. So the implicit update is for the electromagnetic fields and the electrostatic field. So there's two implicit updates. Particles are not implicit.
Okay. They're explicit.
Right.
Okay. Is it possible to add a DC magnetic field bias to the ICP simulation?
That is a good question. And the answer is yes. It should be possible.
Okay. We have time for a few more. We have, can this be used to simulate RF pre-ionization in a toroidal device?
Sure. Yes, it can be. We haven't tried it, but it should be possible to simulate that device.
Okay. In principle. Can you bypass dielectric relaxation time, given that you also solved explicit Poisson solver?
The Poisson solve is actually implicit. Can you repeat the question?
Can you bypass dielectric relaxation time, given that you also solved explicit Poisson solver?
So yeah, the Poisson solver is implicit. That's not, yeah.
Okay. What are the pressure limits for these simulations? And what was the pressure in the simulation shown?
Pressure limits, it doesn't really have any limitations. The simulation that we showed has a 100 millitorr pressure, so it's pre-collisional. And the use case for using a kinetic code would be to run at lower pressure. Higher pressure, you have to resolve the collision frequency, which can become computationally expensive.
Right. How large of a mesh size and particle count can I simulate, and how many cores are needed? For example, how many cores are needed to handle 1 million particle solves?
We showed that you can solve it you can use the solver for a pretty small mesh on a laptop, but it scales. So you can run this on cluster on multiple cores, multiple nodes. So really the solve itself is scalable. Question about how many cores and particles, it's standard for what VSim can already do.
Right.
I don't know the number right off the top of my head, but it's commensurate with our current capabilities.
Sure. How well does the nonlinear implicit solver converge for large time steps?
Thank you for that question. We see convergence in less than 10 iterations for pretty much all of our testing, whether resolving large time steps or short time steps. It so far has been converging in a pretty short amount of time.
Okay. We have one more time, I think, maybe for one more. Can you use port boundary condition with the implicit EM solver?
Yes, we can. Something we haven't tried, but it should be doable.
Okay. Gosh, these have been some great questions. I'm sorry we don't have time to get to all of them today. As we go ahead and wrap up here, I want to remind everybody that if you would like to evaluate this new capability, please visit our website and either fill out our request evaluation form or send us an email directly at sales@txcorp.com. That's txcorp.com. Also want to let everyone know that we have our user summit coming up in October. That is an event that we run every year. We will have a series of online presentations that you can join from anywhere, where we present some of the latest research and use cases of our software from both internally and our own engineers and scientists here, as well as from our research community and the VSim users that we have around the world. On that note, I also want to let everyone know we will be putting this video up on the TechX YouTube channel. It'll take us just a few days. We're going to do some post-processing, but it will be available and we will send out a notification by email on that as well. And I just got real quick, and I want to let everyone know that user conference it is free and you'll be able to join those webinars from anywhere. More information on that should be coming by email next week. On that note, thank you again so very much. This has been such a great presentation, great questions today. I'm very excited that you all decided to join us, and we look forward to helping you all as you evaluate this latest release of VSim. Thanks so much, everybody.